we're in business. Okay, so a sub n is equal to n times n plus 1. I think parts C and D are kind of similar. All right, so that means a1 is equal to 1 times 2, which is 2. And a2 is equal to 2 times 3, which is 6. And a3 is equal to 3 times 4, which is 12. And do a couple more. Next one is 20, and then 30. Right? So we want to define each term of the sequence in terms of a previous term or maybe a couple of previous terms. Doesn't matter how many. I think we might be able to do it. Oh, let's see. No, I don't think that's going to work. Okay. So here's what I notice. I think this is okay. This is the kind of thing you look for. So to get from the first term to the second term, you add 4. And then to get to the next term, you add 6. And to get to the next term, you add 8, right? So the amount by which they're increasing is increasing, right? So I think if you look, you can pretty easily see the relationship between n and the amount by which it's increasing, right? To get from A3 to A4, we went up by 8. To get from A2 to A3, we went up by 6. To get from A1 to A2, we went up by 4. So I think what you can do, well, you have to do an initial one first. You have to say that A1 is 2. And then for any n bigger than 1, I think you can say that a sub n is equal to a sub n minus 1 plus what? 2n! Good. Does that make sense to everybody? This number is always 2 times this number. That's a pretty nice, simple relationship. Is that good? Make sense? Questions? Okay, take that in for a half a minute while you think about think about letter D. I think letter D is kind of similar. Might be just a smidge more complicated. Just a smidge. Is there glare right here? How about now? Oh, you can look on there. I don't think there is. I don't see any anywhere. On my face. Should be okay. All right, so that's a really easy, well, everybody's familiar with perfect squares, right? 1, 4, 9. Oh, whole thing is glare. No, not really. You know what we need? One of those tablets that you can write on instead of the board, right? That might be the next thing to think about. Okay. How about here? Hello. I can't really see that either. You can kind of see it? Okay. Well, I'll try to stick with over here then. All right. 1, 4, 6, 9. 1, 4, 9, 16. Okay. So go up by 3, go up by 5, go up by 7. Oh my gosh, that's really similar to the last one, isn't it? So you just set a1 equal to 1, and then for n greater than 1, you say that a sub n is a sub n minus 1 plus 2n. Is it plus 1 or minus 1? Let's see. So to get to 4, you need a 7. To get to 3, you need a 5. I think it's minus 1, right? For n greater than 1. That seem doable? All right, so in case you missed the memo last time, we're minutes away from the end of 5.3, which is all I'm going to do in Chapter 5. And so I'm going to take your Chapter 5 homework next Tuesday, which is the 22nd. Okay, so all of that homework is already posted. So by then you'll get your exam back, definitely. So I'll hand you one thing, you'll hand me something else. Okay. Oh, by the way, I haven't forgotten that I got homework from you at the exam. That homework, I figure, is not a big rush because you already took the exam on that. You're really not in a hurry for the feedback, right? Okay. So priority number 1 is the exam. And then priority number 2 will be the newer homework, because I'll get that back to you before you take exam 2. All right, Fibonacci numbers. So we talked about Fibonacci numbers a little bit. So they're defined by, the first one is 0, second one is 1, and they number them starting at 0, which is kind of annoying, because it makes it hard to talk about the nth one. All right, so I guess I'll go over here. All right, so I remember, sorry, erase the memo. There it is. So I remember we talked about Fibonacci numbers once before because that's a classic recursion example. F0 is 0, F1 is 1, and then after that just add the last 2. 0 or 1 plus 0 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 5, 8, 13, 21, etc. All right? I can't wait until we get to, I still don't know what chapter number that is, but later on we're going to solve recurrence relations, which means take a recursive definition and find an explicit formula for it. And the one for Fibonacci numbers is surprisingly ugly. Okay, so here are some of the things we're going to do with Fibonacci numbers. Prove that the sum of the squares of the first n Fibonacci numbers is equal to f sub n times f sub n plus 1. So that's kind of a surprising thing. I think it's worth just looking at the first few examples of that. All right. So here's what it's saying. If you take the first few Fibonacci numbers and square them, for example, f sub 1, that's going to be boring. F sub 1 squared is supposed to equal f sub 1 times f sub 2. Well, f sub 1 is 1. And f sub 1 and f sub 2 are both 1. So that works. Let's skip ahead to, why don't we skip ahead to f sub 4? f1 squared plus f2 squared plus f3 squared plus f4 squared. Okay, starting at f sub 1. So we go 1, 1, 2, 3. You add up those squares, and that comes out to 9 and 4 is 13, 14, 15. which is also equal to 3 times 5, which happens to be f sub 4 times f sub 5. So what this is saying is that that's always supposed to work. Okay? So here's what I'm going to do. I'm going to write this down, and then I'm going to turn off the projector so I can use this space. All right? f1 squared plus f2 squared plus yada, 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 up to f sub n squared. That's always supposed to equal f sub n plus f sub n plus, or times f sub n plus 1 when n is a positive integer, so for n greater than or equal to 1. And now, yeah. So now hopefully we'll be able to read that on here. Okay. All right, so this is a statement that's supposed to be true for all positive integers, which means that we should probably prove it by induction. Yeah, any statement that's true for all positive integers is usually proved by induction. And I think we can use mathematical induction. I don't think we need strong induction. Okay, the basis step we already did. Did it over here somewhere. Show it's true for n equals 1. Well, the left-hand side is just f sub 1 squared, which is 1 squared. And the right-hand side is f sub 1 times f sub 2. And those are both equal to 1. Right? Okay. So now the inductive step. Assume that f sub 1 squared plus f sub 2 squared plus yada, yada, yada plus f sub k squared is equal to f sub k times f sub k plus 1 for some positive integer k. We need to show that f sub 1 squared plus f sub 2 squared plus yada, 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 f sub k squared up to f sub k plus 1 squared. We need to show that equals f sub k plus 1 times f sub k plus 2. All right? This up here is p of k. This down here is p of k plus 1. Show that this implies this. All right. So after you've done a few proofs by induction, you start to notice that there's kind of a pattern. So I'm going to take my f sub 1 squared plus f sub 2 squared plus blah, 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 f sub k squared plus f sub k plus 1 squared. And by the inductive hypothesis, those terms there add up to f sub k times f sub k plus 1. Don't forget the last term. Got to carry that along. So we need to show that that thing somehow is equal to this. Okay. Well, look what happens when you factor out an f sub k plus 1. Factor out f sub k plus 1, you're left with an f sub k and another f sub k plus 1. And I claim, and I want you to think about why this is true, I claim that this is definitely equal to that. So I'm going to say because, and I want you to think about how would you finish that sentence. F sub k plus 1 times f sub k plus f sub k plus 1 is equal to f sub k plus 1 times f sub k plus 2. Why is that? In other words, somehow I was able to replace this with this. It's the first time we're doing any kind of proof with Fibonacci numbers, so if you don't see it right away, don't panic. Think about how are the Fibonacci numbers defined? How do you make them? How do you make Fibonacci number k plus 2? What do? You add together what? Fibonacci numbers. K and k plus 1. These are the previous two Fibonacci numbers. Right there. So of course this and this add up to this. So how should we say that? Because Fibonacci? Because of definition of Fibonacci numbers. That's it. Done. It's proven. I have noticed that a lot of these proofs with Fibonacci numbers sometimes work for what we call Fibonacci type sequences. A Fibonacci type sequence means start with any two numbers you want, like, for example, 7 and 11. And then just make the rest by adding two together. So 7, 11, and then 18, and then 29, and then 47. So it's a totally different sequence. But a lot of these properties that you can prove for the Fibonacci sequence work for Fibonacci-like sequences. I don't know if this one does. The way to tell whether it's going to work or not is in the basis step. I'm pretty sure this one won't. But a lot of them do. Make sense? Let's see. Is that all I have? That's it.
So it was proven using, how was it proven by the definition? Where was the definition?
Where was the definition used? By saying that this is equal to this. Because this is the kth Fibonacci number. This is the k plus first Fibonacci number. So picture extending the Fibonacci sequence, listing a whole bunch of numbers. This is k. This is k plus 1. This is k plus 2. And the way you make Fibonacci numbers is add the previous two to get the next one.
So, okay, and we wouldn't have to state it? Like f of k is equal to k minus 1 plus f of k minus 1.
Oh, you could if you wanted to be extra clear. Yeah, so where did they state that? I think the definition they gave, okay, so what did they say? They said f of 0 was 0, f of 1 was 1, and then f sub n was equal to f sub n minus 1 plus f sub n minus 2. So yeah, if you want to be extra clear, you could say it's that definition replacing n with k plus 2. Yeah, that wouldn't hurt. Yeah, this is the definition right here for n greater than 1. Okie dokie. So take that in for another half a minute or so. I'm going to bring up Chapter 6. So again, right here, draw a line. This is all the homework I'm going to collect next Tuesday. But as soon as you're finished that homework, you'll want to start on the new stuff. I'll have to look in my records and see. Trying to remember what was the last section we covered on Exam 2 last year. I want to say it was all of Chapter 6 and maybe like the first section of Chapter 7. I may or may not do the same thing. We'll have to see. Anyway, it's going to come pretty close to the end of Chapter 6. And Chapter 6 is, I'm just curious. Oh, only 3 sections. Geez, okay. So we're probably talking, I don't know, not the week we come back from break, and probably not, well, I don't know. Maybe like Thursday of the following week, but I don't know. We'll see. It's only 3 sections. That's not going to take long. All right, counting. This is one of my favorite things. And it sounds kind of funny when you first hear counting. It's like, well, what are we going to do? Count things? 1, 2, 3, 4, 5? Okay. It's for counting things where 1, 2, 3, 4, 5 doesn't work, right? Big sets of things. Like how many different Powerball tickets are there? Remember a few months ago, the Powerball jackpot was like $700 gazillion. I even broke down and played. You know what? I should make an example of that. Here's an interesting probability question. Where do we do probability? Maybe it's in the next chapter. So I bought 10 Powerball tickets. What's the probability that you buy 10 Powerball tickets and don't match a single number on any of the 10 tickets? Well, I can tell you it happened to me, so it's definitely possible. Yeah.
Interesting thing about that, they actually made the odds worse to make more people play.
Really?
Yeah.
Oh, you're right. Yeah, they haven't, every so often they change the number of numbers, right, that go into the thing they pick them out of. Yeah, it used to be 40-something, and then it was 50-something. Yeah, you're right. Yeah, because then they can build up the jackpot for a longer period of time. And, yeah, that was actually very smart of them. Sure, yeah. Yeah. The higher it gets, the more people play, like by a lot. Okay, so we'll do some fun Powerball things when we get there. All right. So here's an example counting problem. Suppose that a password on a computer system consists of 6, 7, or 8 characters. Your password has to be 6 to 8 characters. Each of these characters must be a digit or a letter of the alphabet and must contain at least 1 digit. So the question is, how many passwords are there? So if somebody's trying to develop some kind of brute force hacking thing, how many possible passwords might they have to try in order to hack in? All right. And the answer is, well, you know that a lot of systems now make you use a special character and all this other stuff, and so they've made that harder and harder to do. Right? Yeah?
Non-negative numbers?
Non-negative numbers. That's interesting. Well, I guess the negative sign would count as a special character, right? Okay. Yeah, so when they say numbers, I think they mean digits, right? Yeah, 0 through 9. All right. So the first thing that goes into this, just to build up to where we need to be for the for this password problem, suppose that a procedure can be broken down into a sequence of 2 tasks. If there are n1 ways to do the first task, and for each of those ways of doing the first task, there are n sub 2 ways to do the second task, then the total number of ways to do the procedure is n1 times n2. So talking about passwords, imagine there was such a thing as a 2-character password. And the first character had to be a letter, and the second character had to be a digit. The number of different ways to make those is not very many. You could hack into that in some fraction of a second. You have 26 choices for what to put there, and 10 choices. See why it's 10 and not 9? Yeah, 0 through 9 is 10 different digits. And so the total number of passwords that you can make that are a letter followed by a digit is only 260. If you allowed for a digit followed by a letter, that would be another 260, but that doesn't help too much. All right? But that's the idea. That's the idea. And it extends to more than 2 tasks, by the way. If you needed a digit or letter, digit, that would just be 26 times 26 times 10. So now we're up to 6,760. Right? No, not yet. Yep, that's all coming. All right, make sense? See why you have to multiply? Because with any of the letters A through Z, you can put any digit. So we're talking A0, A1, A2 through A9, and then B0, B1, B2, 26 times 10. Okay, this is a little harder to explain. If a task can be done either in one of N1 ways or in one of N2 ways, oh, I know how we can do this. Where none of the set of N1 ways is the same as any of the set of N2 ways, then there are N1 plus N2 ways to do the task. So imagine even worse. One character, which can be a letter or a digit, 26 plus 10 choices. That's all that's saying. Now, I have to warn you that when we get to a certain point, it may not always be obvious when do you multiply and when do you add. All right? I think it's pretty obvious with this kind of stuff, but it won't always be. So I'm just giving you a heads up. Okay, we're getting to some better examples because you know me, I steal the examples right out of the book. The even-numbered problems that I don't assign become examples. Okay, an office building contains 27 floors and has 37 offices on each floor. How many offices are in the building? Should I multiply or add? I should multiply, right? That one's pretty easy to picture, right? Here's your building with 27 floors. This is why mathematicians don't design buildings. And then 37 offices. Almost looks like a multiplication table. 27 times 37, which is, help me out, like 800 something? What is that? How many? Yeah. 999. Interesting. Didn't see that coming. All right, 999 offices. All right. 4 major auto routes from Boston to Detroit and 6 from Detroit to Los Angeles. How many major auto routes are there from Boston to Los Angeles via Detroit? This almost makes me think of graph theory, which we're going to be doing towards the end of the semester. Okay, I guess I should try to be geographically correct here, sort of. Put these things in the right order. So you have 4 routes going from Boston to Detroit. number them, let's say, little a, little b, little c, little d. And then 6 routes going from Detroit to LA. And I'll number those 1 through 6. That would be another multiply one, right? You can pick any one of these and put it with any one of these. So you could do A1, A2, A3 through A6. You could do B1, B2, B3, B6. 4 times 6. 24 different routes. Easy, easy, right? What else we got? Oh, bit strings. Okay. You know about bit strings? I didn't really know about bit strings until I had to teach this class. Bit strings are just strings of zeros and ones. They're basically binary numbers. All right. So I bet all of you know that a bit is either a 0 or a 1. That replaces the word digit when you're in binary. Okay. Not counting the empty string. All right. So length 6. Good. Yes. So put a 0 or a 1 in each one of these spaces. So you have 2 choices for what to put in each space. 6 spaces, 2 times 2 times 2 times 2 times 2 times 2. 2 to the 6th. And that's also going to be for length 5, right? It says 6 or less. 2 to the 5th, 2 to the 4th, 2 to the 3rd. Oh, this is a great example where you have to do some multiplication and some addition. Okay? Use the multiplication rule or the product rule to get each one of these answers. And then to get the total answer, back up to that sum rule again because I want you to see how that's used here. So the task of making bit strings of length 6 or less can be done either by making length 6 or by making length 5 or by making length 4, right, et cetera, and that's why you have to add all of these together. Yeah. Right, yeah, I see where you're getting that. It kind of does go along with a power set. Let me just write this down and then we'll think about that a little bit. So this is, and there's a short way to do this. 64, let me see, that's, well, what's messing me up is that I don't have the 2 to the 0. But 2 plus 4 is 6, plus 8 is 14, 34, 66. Somebody's going to have to check me on this. Is it 130? I missed a 32. Okay. 64, 32 is 96, 16 is 112. That seems too big. 26, that sounds, yeah. There we go. Yeah, so Peter said something about power sets. Yeah, and there's kind of a natural way to look at bit strings and subsets next to each other. So imagine you're looking at the bit string 0, 0, 1, 0, 1, 0. If you have a set with 6 things in it, this particular bit string goes along with the subset C and E. So the bit in each position tells you whether the corresponding element is in the set or not. Okay. And so we know that this set has 2 to the 6th subsets, and we know that there are this many bit strings of length 6. Yeah, so there's a nice one-to-one correspondence. This bit string means this subset, and you can do that for any bit string. Good. All right. Excellent. All right, is that it for examples on that one? Yes. Okay. Subtraction rule, this is also called the complement rule. And by the way, any of you that have taken statistics, Math 10, you'll be sitting pretty for a lot of what we do in this chapter. Not all of it, but a lot of it. So this is called, this is usually called the complement rule. And in fact, we might call it that when we get to probability. Complement. Remember we talked about complements of sets? Okay. So if a task can be done in either n1 ways or n2 ways, then the number of ways to do the task. Oh, okay. Never mind. I'm sorry. I'm thinking of something else. This is not the complement rule. I saw subtraction. No, the term that I always call this rule is that. Principle of inclusion-exclusion. I feel like when we talked about sets, did we talk about this rule at all? That the number of elements in the union of two sets is equal to the number in A plus the number in B minus the number in the intersection. Did that come up when we did sets? I can't remember. Well, let's say it didn't. That's what this is saying. All right, if a task can be done in either n1 ways or n2 ways, this is a generalization of the sum rule that you saw a few slides ago. Subtraction rule is a terrible name for it. The number of ways to do the task is n1 plus n2 minus the number of ways to do the task that are common to the two ways. All right, we need an example of that. I will almost always call this the principle of inclusion-exclusion, because that's what it's usually called. Oh, there it is. Oh, that might be part of, okay. I got my notation mixed up. I forgot which class I was talking to. Yeah, we use that notation for the number of elements in a set. Right? Okay, let me see if I have an example of that. There we go. Okay. Oh, this is perfect. So let's do, how many? Let's do just maybe a couple of parts of this. And it doesn't necessarily have to be A and B. Let's do A and C. A and C. And then during the break, think about the other parts. Some of these are kind of hard. Oh, I should try to find this article for you guys. I bet I can find it during the break. So yesterday, in honor of Pi Day, some math professor somewhere cooked up 3 problems, and some website or something had a contest, and it was sponsored by Pizza Hut, where the first person to solve these 3 problems and post them on some blog somewhere got free food for 3.14 years or something from Pizza Hut. So I read the 3 problems, and I'm totally intrigued by the first one. I should tell you guys about it. Maybe I'll do that after the break. The second one I kind of understand, and the third one I think might be just kind of poorly stated because I don't really understand the third one. Anyway, I'm thinking about the first one. I'm not trying to get the free food. I'm just curious. Okay. All right. So number 4, how many positive integers less than 1,000 are divisible by 7? So who are we talking about? 7, 14, 21, 28, etc., etc. So how could you count that? What would you do? Might be able to do it by programming. I don't think that's the most efficient way, though.
I'd make a 4 lead.
So what could you do to count the number of integers less than 1,000 that are divisible by 7? Take the 1,000 and the 7 and do what with them? I heard power. 7 to the power 1,000?
Oh wait, no, I know. Find the biggest number you can multiply by 7. That goes up to 1,000.
Okay, yeah, that'll help.
And then you do
I want to say that that number is, I want to say it's 142. Yeah, the biggest number that's divisible by 7 that's less than 1,000 is 994. But you don't even have to figure that out. Just take the 1,000 and the 7 and do what? Divide. Thank you. Okay, now when you divide 1,000 by 7, you're going to get a decimal.
142.
Point something something. So just round that thing down, floor it. Right? 1,000 divided by 7, floor is 142. That's how many of those there are. The first one is 7 times 1, the second one is 7 times 2, and the last one is 7 times 142. Yeah, just divide. Okay. So I'm going to skip over to part C. The number of positive integers that are divisible by either 7 or 11. Well, tell me what you think about this. So to count the number that are divisible by 7, you do the same thing. And then to count the number that are divisible by 11, you would do this. Okay. This is how many are divisible by 7. This is how many are divisible by 11. Okay. Now, is there any problem with that? Could we just add those two together? What is 1,000 divided by 11? Just give me the whole number part. Should be 90 something?
90.
90.90909. So 90. So is 232 the answer? There's a problem with that. What's the problem? There you go. There are a whole bunch of numbers that are divisible by both 7 and 11. Well, maybe not a whole bunch, but there are some. Like 77. The number 77 is counted here, and it's also counted here. The number 154 is counted in both of those places. So we have to take all of those out. That's what the principle of inclusion-exclusion says. So this is how many are divisible by 7. This is how many are divisible by 11. And now we have to subtract the number that are divisible by both. Well, it just so happens that numbers that are divisible by both 7 and 11 are divisible by 77. Okay, so what is 1,000 divided by 77, the whole number part? 12? Okay, so there's 12 numbers we have to take out because we counted them twice. So that comes out to 220. All right. So that's a good start. So why don't we take 10, including a few minutes to think about B, D, E, and F. Okay. There we go. Okay. So letter B. So I think you end up using some of the same numbers that we used in A and or C, right? What do? You take the ones that are divisible by 7 and do what? Subtract the ones that are divisible by 77, because those are exactly the ones that are also divisible by 11. And so that comes out to be 142 minus 12, so 130. Good. Okay, letter D. I bet somebody got letter D. It's E and F that are sort of different from what we've done so far. Okay, that are divisible by exactly one of 7 or 11. So we want to count things that are divisible by 7 or 11, but not by 77, right? So there's probably a couple different ways you could do this. You could take the ones that are divisible by 7 and add the ones that are divisible by 11. And then what do you have to subtract? The ones that are divisible by 77. But that's going to give you the same answer that we got for C. So how do you make it different? Well, unless they're asking the same question, which would be kind of tricky. No, I don't think so, right? Because in part C, we were counting. See, here's the thing. This gives me a chance to explain principle of inclusion-exclusion a little more. Let's say that these are your two sets, and they overlap. So these are numbers that are divisible by 7. These are numbers that are divisible by 11. So this set's going to include 7, 14, 21, 28, etc., etc. This is going to include 11, 22, 33, 44, etc. And then you're going to have numbers like 77 here. The reason for the formula in principle of inclusion-exclusion is when you count all the numbers that are divisible by 7, you are counting all of these, including those. When you count the ones that are divisible by 11, you're counting all of these, and you're counting that again. So the reason you have to subtract is so that those are only getting counted once. But in letter D, how many times do we want these ones to be counted? Not at all. So don't just take them out once. Take them out twice. That's how I would do it. Take them out twice. And then you're not counting those at all. That sounds horrible. 142 plus 90 minus 24 this time, right? So that's going to come out to 208. Is that right? Does that make sense? All right, so now we get into something a little different. How many positive integers less than 1,000 have distinct digits? Okay. Well, you have to be careful. You have to be careful when you're counting numbers. And here's the pesky part. It's very, very easy to count 3-digit numbers with distinct digits. I'm going to copy down what it says, and then I'm going to mute the picture. Distinct digits. How many have distinct digits? And this is where we're going to do a little bit of that backwards counting like you saw me do in the Pizza Hut problem over there. I'm going to start by counting 3-digit numbers. Only 3-digit numbers. Three-digit numbers with distinct digits. Okay. Well, if it's a 3-digit number, the first digit cannot be a 0, right? If a number is going to be written 096, we just don't bother writing the 0, right? So if there's going to be a 0 anywhere in that number, it has to be either here or here. Okay? So I think what we want to do is maybe start at the right end and say that there are, first, 10 choices for what to put there. Oh, I'm going to have to think about this for a second. Okay, that can be anything 0 through 9. This, oh, this is a little more complicated than I thought. You have 9 choices there. It can't be anything that you used over here. So if this digit is a 9, you can only use 0 through 8 here. Okay. Now, where it gets a little tricky is filling in the last digit, and I thought starting at the right side would make this easier. Okay. This digit can't match anything that you used here or here, and it also can't be a 0. Okay. And so now we get into a slightly complicated thing where we have to break it down even further. Okay. Because I may or may not have used a 0 over here. Okay? So I think what we might want to do, let's see. Let me think about this for a second. Break it down into a couple of subcases. I'm just trying to think what they should be. Okay. Well, if you don't use any zeros at all, that's easy. Let's do it this way. Okay, so no zeros anywhere. Well, you have 9 choices for what to put here. You have 8 choices for what to put here. And you have 7 choices for what to put there. Okay. So that comes out to 9 times 8 times 7, which is what? 504? Does that seem okay? All right. The second possibility is that there is a 0 in, say, the ones digit. Okay, so that's a 0. You have one choice for what to put there. And now I think that now you want to count backwards. So now fill in this number with anything except 0. So you have 9 choices for what to put there. And then fill this in with anything except for the 0 or what you put here. So there's 8 choices for what to put here. 8 times 9 times 1 is 72. Okay. And then I think there's also going to be 72 that have a 0 in the tens digit. I forgot how complicated this was. So this is case 1, case 2, case 3. Okay, so that one is a 0, one choice. You can put anything over here except 0. And you can put anything over here except for the 0 or what you put there. So that's also 72. Okay, so far we are at 504 plus 72 plus 72, which is 648 three-digit numbers with distinct digits. Yeah?
Couldn't you just do 9 times 9 times 8?
Probably. 9 times 9 times 8 is 648, isn't it?
Yeah, that's what I did.
Yeah. Walk me through that.
Oh, because since the first one can't be a 0,
Right.
so that's 9. And the second one can be a 0, but then since you get rid of
Oh my gosh! Yes. Nailed it. Good. Okay. Yeah, he found a much simpler way to do it. This happens to me sometimes with counting. I don't think of the easiest way first. So he's saying just pick this one first. It can't be 0. Pick this one second. This one can be 0, but it cannot match the first digit. Oh my goodness. And then this one just can't be the same as this or this. That's so much simpler. Thank you. All right. I took the scenic route. Okay, so let me try now, because I would have probably done the same scenic route with the 2-digit numbers. Okay. All right, so there's 3-digit numbers. Now the 2-digit numbers, they should be easier to count. Okay. This one can be anything except 0. So 9 choices. This one can't be the same as the first. But it could be 0. 9 choices there. So there should be 81 of those. Good. And then, this is a little weird. We're talking about integers that are less than 1,000. Do 1-digit numbers have distinct digits?
Yes.
Yes, they do. They don't get repeated, do they? Right? The number 5 has distinct digits. So they all have to be counted. Oh, and you know what? I need to read the problem. I think it did say positive integers, right? Okay, so we don't count 0. Okay, so there's 648 of those. There's 81 of these, and there's 9 of these for a grand total of 738. 738 integers less than 1,000 that have distinct digits. All right. Okay. Now, does that make sense? I think that all that together is the simplest way, right? Not all this stuff, but your way plus this and this. I don't think you can come up with that 738 just by doing something times something times something. I don't think you can do that. All right. Okay. Now letter F. Will this be a lot harder? We want to know how many of those have distinct digits and are even. Okay, so in other words, how many of those 738 numbers end in a 2, 4, 6, 8, or 0? That, you know what? That's probably correct. That's probably correct. So I heard somebody say divide by 2. Half of them must be odd and half of them must be even. Let's call that a conjecture. I'm a little nervous. I'm not totally 100% convinced. I'm about 75% convinced that out of all the numbers that have distinct digits, half of them are even and half of them are odd. Well, yeah, I'm about 80% convinced. 738 divided by 2. Let's see if we can get that answer some other way. So what does that come out to? 369. 369 are even, 369 are odd. Well, let's see. Let's start with the easy ones this time. One-digit numbers, there are 4. Right? 2, 4, 6, and 8. Okay. I think maybe for these, this is where you do have to break it down into cases now. All right? Because you know that in an even number, the last digit has to be even. Right? The last digit being even will make the whole thing even. And so counting how many choices you have for each digit, well, it's going to kind of depend on a couple of things. First of all, if you use you have to use an even number in the ones digit, and then just don't use that number in the tens digit. It doesn't matter what you put in the tens, as long as it's not a 0, right, for 2-digit numbers. So I think we should probably do it like this. Count the ones that end in a 0 separately. And there are only 4 of those, 20, 40, 60, 80. And then if the number doesn't end in a 0, Oh, wait a second. Oh, yeah. What am I thinking? Everything 10 through 90. Yeah, there's 9 of those. I think I might have been stuck on my Pizza Hut problem. Because this is the kind of thing I was thinking about yesterday. Right. Okay. Yeah, so there's 9 of those. And then, okay, this I think is where you want to do it backwards. If you know your number doesn't end in a 0, that means you have 4 choices for what to put here. That can be 2, 4, 6, or 8. And then how many choices do you have for what to put there? Do you have 9? It can't be the same as whatever you put here. But it also can't be 0 either. So I think you have 8 choices. I'm numbering these 1 and 2 so that you know when you look at it later that that's the order I did them.
Well, the trick is it can be tricky because, nine to start out with, and then they kind of 10 to start out with, they believe they're only 9.
Mm-hmm. See, I think you might be running into, if you try to start at the left end, it gets very tricky because then you break into these cases. Like for example, let's say that the last digit is a 2. This digit can be anything except 0 or 2. If you make this digit a 6, then this one can be anything except 0 or 6. Right? And we're leaving out 0 because we had to count those separately. Okay, because you can't put 0 here. All right, so that gives you 32. 8 times 4 is 32. Okay. So far we have 4 plus 9 plus 32. Okay, now the 3-digit ones. I think we can do the 3-digit ones the same way. Start with the ones that, go ahead.
Because if you did 8 times 5,
Mm-hmm.
it would be 40 instead of 41.
Mm-hmm.
So which number does it exclude if you do it that way?
Oh. If you do, say that again, if you do
8 times 5.
8 times 5. Oh, in other words, let this number be 0.
You're excluding. I agree because I got it a different way. 41.
How did you do it?
I said each digit starting with an odd number, the row is missing an odd number.
Okay. All right, so yeah, you still used cases, you just did different cases, right? Either starting with an odd number or starting with an even number.
Right.
So if you start with an odd number, you have 5 choices, and then the last digit, you have 5 choices, right? If it starts with an odd number, you have 5 times 5 choices. We want it to be even. And if you start with an even digit, you have 4 choices. And then this still has to be even. It could be 0, but it can't be this. Yeah. 25 and 16 is also 41. Okay. Yeah, there's often a bunch of different ways to do these. But I'm still stuck on your question. It could be that that we could have done it that way and there's just some number that we're missing. It could also be it's just a coincidence that 8 times 5 happens to be 1 off from this. I'm not sure. I would have to think about it. Okay. 3-digit numbers that have distinct digits and end in an even number. So why don't we try this same thing again? There's the ones that end in 0. Okay. All right. So you have 9 choices for what to put here and 8 choices for what to put here, right? This can't be a 0, and this can't be a 0, and it also can't be this. So 72 of those. And then there's the ones that don't end in 0, and we should count those starting from the right end. Four choices for what to put there. 9 choices for what to put here. This one can be a 0, but it can't be that number, right? And then you have 8 choices for what to put here. And that comes out to 72 times 4, which is 288. Is that right?
Yeah.
Okay. So grand total, is it 369? 4 plus 9 plus 32 plus 72 plus 288. Is that 369? Wait a minute. That seems weird. That's a lot more than 369, isn't it?
Yeah, the last digit isn't
That's 360. That's 382. I want to say 395. Is that what those add up to? 13, 45. 45 and 72 is 117, 117 and 288. 405? Okay. All right. Well, I'm going to have to think about, I'll do this before next time I see you. I'm going to have to think about why isn't that 369? Like I said, I was only 80% convinced that it should be 369. All right. That's the idea. That's the idea. I'm also going to double check that, though, just to make sure. All right. Well, let me see. Where are we? Oh, okay. Let's do number 5, and then I think we can call it a day. How many bit strings of length 7 either begin with 2 zeros or end with 3 ones? So that's a good inclusion-exclusion problem. Mm-hmm. All right. So why don't we just give these set names? We'll say B is the set of bit strings that begin with 2 zeros. I think I might have lost some of you on the stuff there, so I want to bring everybody back now. This one's easier. And we'll say set E is the set of bit strings that end with 3 ones. Okay. So they want to know how many of these things are in either B or E. So this is an inclusion-exclusion. We'll count the number that are in B, add the number that are in E, and then subtract the number that are in both. Okay. So how do you count B? So let's say here's our bit string, 1, 2, 3, 4, 5, 6, 7. And it begins with 2 zeros. So how many choices do you have for what to put here? Strings are much easier than numbers because they are allowed to start with 0. That makes them so much easier. All right, how many choices? 1 choice. It has to be a 0. How many choices here? Has to be a 0. And then what about these? Not 10. These are bits. 2, right? 0 or 1. So there are 2 to the 5th of these. Right? How many are in E? 2 to the what? To the 4th, right? You have 1 choice, 1 choice, 1 choice for what to put there. Those all have to be 1s. But then 2 choices for what to put here. Right? But then didn't you count some stuff twice? And there's some stuff we got to take out. I think there are a few bit strings that begin with 2 zeros and end with 3 ones, right? Okay. 0, 0, 1, 1, 1. So you get to pick these 2. 1 choice, 1 choice, 1 choice, 1 choice, 1 choice. 2 choices for these for a total of 4, right? Because those middle bits could be either 0, 0, 0, 1, 1, 0, or 1, 1. So this is 2 to the 2nd. 2 to the 5th is 32. 2 to the 4th is 16. 2 to the 2nd is 4. So there are a total of 44 bit strings of length 7 that are like that. All right. And I think that's a nice full day. All right. So we'll